In this video, I'm going to answer some key questions about Mohr circle that we really haven't answered. For example, we plot IXY and IX on one side of the circle, but 180 degrees apart from that on the circle, we plot IY and minus IXY. Why is that? Why is 2 theta on Mohr circle correspond to theta on the original area? Some of the questions like that is what we're going to address. So these are some key questions. How does Mohr's circle relate to the transformation equations? So we derive transformation equations. We use them to calculate I max and I min. We use them to calculate I at different thetas. We use Mohr's circle to do the same thing. Let's try to tie those together more closely so you can understand them both better. I gave you 6 different transformation equations, but how many do you really need? We'll talk about that. When you plot Mohr's circle, you plot IX and IXY on one side of the circle, but then 180 degrees apart from that, you plot IY and minus IXY. Why is that? We'll talk about that. Where does the 2 theta p equation come from? So we use the 2 theta p equation to calculate the angle from the x orientation to the nearest principal, either I max or I min. Where does that equation come from? What is the defining triangle for Mohr's circle? When you really think about it, Mohr's circle really boils down to a triangle. And let's talk about that defining triangle. Another question, why is 2 theta on Mohr's circle correspond to theta on the original area? We'll talk about that. And finally, we'll talk about the invariance property where Ix plus Iy is equal to Iu plus Iv, which is equal to I min plus I max. And why is that? So I'm just going to create a really simple example with some simple numbers that we can work with. So here's a simple S-shape beam. I didn't even give you the dimensions for these. But if you look at this shape, you can tell that Ix is going to be larger than Iy because the area is all closer to the y-axis and it's farther from the x. And you can also tell that Ixy is going to be positive because the shape lies in a diagonal that goes from quadrant 1 to quadrant 3. And that's a positive Ixy. So I just chose some numbers. So I chose Ix is 12 inches to the 4th. Iy is 4 inches to the 4th. And Ixy is positive 3 inches to the 4th. So to set a Mohr circle, I average is 12 plus 4 divided by 2, which is 8 inches to the 4th. The radius is Ix minus Iy over 2 squared plus Ixy squared. Well, you get 4 squared plus 3 squared, and so the radius is actually 5 inches to the 4th. So I did that on purpose just to get some easier answers to work with. So if you plot Mohr's circle for this shape, I average is 8, I max is 13, I min is 3. Our x face plots at 12, 3, which is up here, and our y face plots 180 degrees from that, which is 4 and minus 3. So why again does I negative Ixy plot with Iy? Well, we'll talk about that. Notice that on our original shape, that if you go counterclockwise from the y, you should get to I min. And if we come down here to Iy and go counterclockwise from Iy, that takes us to our I min. And so that kind of corresponds to our shape. So remember, all of the points on this circle are combinations of moment of inertia and product of inertia. And moment of inertia is basically our Ix, our Iy, our Imax, our Imin values. They're all along the x-axis. And the vertical axis is Ixy, or product of inertia. And so at every orientation, we're going to have a combination of a moment of inertia and a product of inertia to plot along this circle. All of those points can be calculated from two transformation equations. I call these the two theta forms of the equations. And really, you just need two. I gave you a total of 6. So if you actually go to our transformation equation pages, there's a total of 6 equations here. What I call the theta forms of the equations and what I call the two theta forms. These are basically the same as one another. We've just did a trig substitution to convert the theta form to the two theta form. One of the things I'll show you in this particular handout is that you've got an IU and an IV, or an IX prime is in an IY prime. So these guys are 90 degrees away from one another. But we really only just need one of these, and we just put in the correct theta. And so if we put in theta equals 0 for this guy, and if we want I90, we just take the same equation and plug in theta is equal to 90. We don't need this second equation. So really, out of all of these 6 equations, it really boils down to just this one and this one. And from these, we can do everything. And from these, we can derive Mohr circle as well. So these are really the two. This one and this one are the only two that you really need to remember. So I repeat those here. So this is the IU equation, and this is in terms of I average, and this is in terms of that Ix minus Iy over 2 term that comes up frequently. And then this is the IUV form of the equation. These two theta forms of the equations are relatively easy to calculate with. And so these are the two that you really need to remember. So if these are the only two equations we need to remember, and if these two equations together give us all of the points on this circle, let's plug in some angles and see what those angles give us. If we plug in, given an Ix, an Iy, and an Ixy, if we plug in theta equals 0, by definition, that should be Ix. And that should be Ixy. So let's try that. So if theta equals 0, we plug 0 degrees into this equation. The cosine of 2 times 0 is 1. The sine of 2 times 0 is 0. And so our moment of inertia equation says that our I at 0 degrees is I average plus Ix minus Iy over 2. If you add these two together, the Iy over 2 cancel out, and you're left with Ix plus Ix over 2, or Ix. So at 0 degrees, we get Ix, which is what you expect. So if we plug 0 degrees into the Ixy equation, then this is the Ixy that will plot with the Ix. If you plug 0 here, sine 2 of 0 is 0. Cosine 2 times 0 of 0 is 1. And so our Ixy at theta equals 0 is Ixy. And that's what we'll plot with the Ix on Mohr circle. So what about 90 degrees? So remember on our original element, we had this S shape, and we had an x-axis and we had a y-axis. Positive theta is measured counterclockwise. Negative theta is measured clockwise. And so if we're looking at the y orientation, we can just plug 90 degrees into our transformation equations. So if we take the I equation and plug in 90 degrees, we get Ix plus Iy over 2, plus this guy times cosine of 2 times 90. 2 times 90 is 180. Cosine of 180 is minus 1. And then we have an Ixy sine of 2 times 90, but sine of 180 is 0, so that drops out. So we're left with I at 90 is Ix plus Iy over 2 minus, because of the minus 1, minus Ix minus Iy over 2. The Ix's cancel, and we're left with Iy minus a minus Iy, which is plus Iy. So Iy plus Iy over 2. So my I at 90 degrees is Iy, as expected. So my transformation equation will give me the correct I at every angle measured from the original x. So what is the Ixy, or the YUV, at 90 degrees? In other words, what is the product of inertia that plots with my Iy when I go 90 degrees from on the original element? What plots with my Iy? So if you take the IUV equation and plug in 90 degrees, sine of 2 times 90 is sine of 180, which is 0. Then cosine of 2 times 90 is cosine 180, which is minus 1. So this term drops out, and my IUV at 90 degrees is negative Ixy. And so this is the guy that plots with my Iy, because both of them are 90 degrees from x. Does that make sense? That's why he plots there. Notice again that 90 degrees on my original element plots as 180 on the circle. It's just a feature of the equations. It's a feature of these equations. So remember, we derived Mohr's circle from these two equations. This is the IU equation. This is the IUV. And warning, I'm actually going to quickly derive the equations again, again, I'm trying to show you the connection between Mohr's circle and the transformation equations. So if we let Ix plus Iy over 2 be I average, and if we let Ix minus Iy over 2 be A, then we can take this first equation and we can take IU minus I average is equal to A cosine 2 theta minus Ixy sine of 2 theta. In the second equation, we can write that as IUV is equal to A sine 2 theta plus Ixy cosine 2 theta. If we square both sides of both of these equations and add them together, we get IU minus I average squared plus IUV squared on our left-hand side. And on our right-hand side, we're going to end up with 6 terms. An A squared cosine squared 2 theta. And then from this guy, we're going to end up with an A squared sine squared 2 theta. When we add those two together, we get this term. We're going to end up with an Ixy squared sine squared 2 theta. From here, we're going to end up with an Ixy squared cosine squared 2 theta. We're going to add these two together, and that's going to be Ixy squared sine squared 2 theta plus cosine squared 2 theta. And then finally, we're going to get two mixed terms, a negative Ixy sine 2 theta and a positive Ixy A cosine 2 theta sine 2 theta term. And they're going to cancel one another out, so they'll be 0. So your right-hand side goes from 6 terms down to 2 terms. And what you're left with on the right-hand side is an a squared term, which is ix minus iy over 2 squared plus ixy squared. Well, if you look at this right-hand side, ix, iy, and ixy are given for a particular problem. So these are known. But this looks like a triangle. This looks like a triangle that has a base equal to ix minus iy over 2, a vertical side, which is ixy. And if you square these two, you get a radius squared term, r squared. And so this right-hand side leads to this triangle right here. And I call this kind of the defining triangle for Mohr circle. So once you understand this triangle, this is the guy that really defines Mohr circle. And just take that radius and just rotate him at different angles, but you end up with basically the same triangle. But if you look at the left-hand side, this is basically the same idea, but now this is at some other orientation from this guy. And so the radius here is equal to the radius here. And so the left-hand side is just any new orientation compared to the original orientation. And so this is basically how we derived Mohr circle. Notice, if you look again at this triangle, if this base is ix minus iy over 2, this implies that there's an iy that's mirrored across from I average, that there's an iy over here. And that total distance from here to here is ix minus iy. And you divide this guy by 2, that gives you this leg here. But if this mirrors over, then by similar triangles, this is ixy, then this has to be minus ixy. And note also that this is 180 degrees apart. And so my iy plots at 180 degrees from ix on Mohr circle, but you know that ix and iy are 90 degrees apart on the original area. So in effect, this also kind of proves that 2 theta on Mohr circle corresponds to theta on the original ix, iy area. And this also proves that negative ixy plots with ixy just because of similar triangles from this definition here. This is our radius, which we saw. We talked about this defining triangle, which we just kind of explained already. This triangle basically proves the 180 on the Mohr circle corresponds to 90 on the original area. Remember also, when we originally derived the transformation equations, theta was the angle on the original area. And of course, iy was 90 degrees from ix. But again, we've seen now that when we plot iy on Mohr circle, iy plots at 180 degrees from ix. And so, again, that's kind of a proof of 2 theta on Mohr circle corresponds to theta on the original area. Finally, we need a theta p equation. And so if you start with the IUV equation, and you recognize that on Mohr circle, the maximum value of the moment of inertia lies on this axis where ixy is 0. And I min lies on this axis where ixy is 0. So you can take this equation and set it equal to 0 and solve for 2 theta p. So when you set this guy equal to 0, you get a tangent of 2 theta p is equal to negative ixy over ix minus iy over 2. And you get this from the equation. You also can get this just from the defining triangle. So if this is our defining triangle, and the base is ix minus iy over 2, and this guy is ixy, then the tangent of 2 theta p is ixy divided by the base, which is ix minus iy over 2. From this triangle, you don't get the sign. You technically need the sign to give you the direction, the proper direction for theta p. So at least you get the magnitude from this guy. And the direction in this case is clockwise, which is the negative direction. So technically it needs the sign negative here. An alternate equation, especially if you have Mohr circle already set up, is if this is I average and this guy is Ix, then this distance is also Ix minus I average. And so you can put Ix minus average in your denominator down here too. So this is like an alternate 2 theta p equation. So again, it really comes down to just 2 transformation equations. And from these 2 equations, we can derive Mohr circle. From these 2 guys, or from the second guy, we can get the 2 theta p equation. One more thing I'm going to show you. Let me see if I'm done with this page. Okay, so one more thing I'm going to show you. I just whipped this up for this lecture. And so basically, this is back to our original case. If we let Ix be 12, Iy be 4, Ixy be 3, for that original S shape, we calculate an average, which is 8, a radius, which is 5, an Imax, which is 13, and an Imin, which is 3. And so if we take these transformation equations and just start plugging in thetas, and remember thetas on my original area, if I plug in theta equal to 0, I should get my Ix and Iy. And I'm sorry, I should get my Ix and my Ixy. And so at theta equals 0, I get 12 and 3. So 12 and 3 plots up here, 12 and 3, when this is my original X orientation. If I plug in 90 into this equation, and I come down here to 90, I get my moment of inertia is 4, and my product of inertia is -3. So 90 on the original area, which really is Iy. Iy is 4. And so 4 plots here, but the Ixy at 90 degrees is -3, which is what I expect. So I've incremented 90 degrees on my original element, and I've plotted all of those points at every 5 degrees on my element, but every 5 degrees on my element is 10 degrees on Mohr circle. And I end up down here at 180 degrees for my Iy minus Ixy. And so this kind of proves that these 2 equations, these 2 transformation equations, as I increment theta on my original area, will compute this locus of IUV points that will ultimately define my Mohr circle. The Excel sheet for this is actually in your project folder, your statics project folder as well, if you want to play with it. So it's actually kind of interesting. One last thing I want to show you, again, tying the big picture together, is one of the key facts about Mohr circle is the invariant principle, which basically means that Ix plus Iy is equal to Imax plus Imin, which is equal to IU plus IV. And if you take the Ix prime equation and the Iy prime equation, which is 90 degrees from this guy, and add them 2 together, this term drops out, this term drops out, and you're left with ix prime plus iy prime, which I would call iu plus iv. That's equal to ix plus iy over 2 plus from here plus ix plus iy over 2 from here. And of course, these equal to ix plus iy. And then this is true at any other orientation. I min, I max, iu plus iv, ix plus iy. They all sum to the same number. If you wrote the cosine and sine squared forms of the transformation equations and added these together, you get the same result. And so that's a useful number that you occasionally find a purpose for, that ix plus iy is equal to I min plus I max, which is equal to iu plus iv. So it's called the invariant property. So these are just, again, a summary of some of the key principles about Mohr circle, how Mohr circle connects to the transformation equations. We use the transformation equation to derive Mohr circle. The Mohr circle is the locus of points of moment of inertia and product of inertia. And so we can literally take the transformation equations, increment their theta, calculate I, moment of inertia, product of inertia points, and those points walk around our Mohr circle. And so we can use transformation equations, we can use Mohr circle. They all give us the same answers, and we should know how to do both.